Let's look at a modeling problem, which is some sort of real-world example that we can use functions to describe more clearly. Okay, so we're going to look at somebody at an amusement park. So a guest at an amusement park spends $30 for admission, food and drink, and then an additional $2 for each ride. So we're going to write a function that describes this, this guest's behavior at this park, because why wouldn't you want a function that describes that? And we're going to restrict the domain, assuming that the person goes on between 0 and 4 rides. Well, let's think about what that domain looks like right now, because you can't go on 1.5 rides. I think parks frown on that. You can't just jump off when you're at the top of the Ferris wheel. All right, so this is a discrete domain, because you can only go on 0, 1, 2, 3, or 4 rides. Okay, so we have two ways of writing this: the boring way and the less boring way. All right, we're going to write it the boring way because this is probably the way you'll most commonly see it. We're going to call this our domain. And we're going to say that it is the set of x's such that x equals 0, 1, 2, 3, or 4. And that is a perfectly valid way of writing that domain. Okay, but if you want to be more fun, all right, the second valid way of writing this domain is we could restrict the set that we're pulling from. We've been saying that x is in the real numbers for all of these set notations, but we could say that x has to be an integer. All right, and that fancy z is a way of saying integer. All right, x is in the set of integers where x is less than or equal to 0 and x is greater than or equal to 0 and less than or equal to 4. If we say that x is in the integers, then when we say x has to be between 0 and 4, we can only include the integers in that interval. So this is saying I can only include 0, 1, 2, 3, or 4. All right, both are fine. I would accept either one on any kind of assignment you gave me, but isn't the green one a little more fun? I think so. All right, so now let's write the function. So this is a classic mx plus b situation. I have $30 that I'm starting with. That's my y-intercept, right? That's my starting point. And then I am increasing by $2 for each ride. So my slope, the amount that I'm increasing by, is 2 for every ride, where x, where the input, we should say where x is the number of rides. Okay, so if I ride no rides at all, then this doesn't matter, and I'm just spending $30. If I ride one ride, then I'm spending $32. You see. All right, so now I have a restricted domain and my function. Let's go. All right, we're going to represent the relation, the function, as a table, as a graph, and as a mapping diagram. Okay, so as a table, here's the x's that are my number of rides, and my f of x, which is the money I spend. If I ride 0 rides, all right, let's go ahead and remind ourselves what our function was. F of x was 2x plus 30. If I ride 0 rides, I'm still spending $30. If I ride 1 ride, 32, 2 rides, 34, 3 rides, 36, and 4 rides, 38. Okay. A mapping diagram takes my domain and maps it to my range. So in my domain, I've restricted it to 0, 1, 2, 3, or 4 rides. That's it. That's all the fun I'm allowed. And then that means my range is going to be $30, $32, $34, $36, $38. So 0 rides goes to $30. 1 ride goes to 32. 2 rides goes to 34. 3 to 36, 4 to 38. So each element of my domain, my x values, gets mapped to an element of my range, my f of x values. And I can do that as a graph too. If I ride 0 rides, I'm spending $30. One ride, what are we counting by? This is $35.40. This is kind of tight here for a little stylus, but that's $32. Pardon my estimating. 2 rides is $34. 3 rides is $36, and 4 rides is $38. You might be tempted to connect to those points, but this is a discrete domain. It is a discrete collection of points. You cannot ride 1.5 rides, so there should be no y value there because 1.5 is not in your domain.